Okay, thank you very much, and thank you for the opportunity to speak to you. I'll be presenting, as was mentioned, a project that's called the Climate Impacts on the Productivity and Health of Aspen. And we call it, for short, CIFA. Everyone else seems to call it CIFA, including ESRD, so we don't really care what you call it as long as you remember it. But anyway, this work was initiated by Ted Hogg, who's a research scientist with the Canadian Forest Service in Edmonton back in the year 2000. So I'd just like to put our work in a bit of a global context. As a lot of you may know, there's been an increasing number of drought-induced tree mortalities from around the world. This is the figures here are from a synthesis paper by Allen done in 2010, and they list some of the Alberta aspen parkland as one of those areas that's experienced some drought-induced mortality. There have been many publications, and some quite recent ones. A lot of these we've been involved with, and I've just listed some of them on the side. In North America, the species that we've been primarily concerned about is trembling aspen. And as you know, it's the species that has the most widespread distribution. And as I've mentioned, it's experienced a number of recent mass tree mortality events. In Western Canada, in the prairies here, most of it's been involved with the aspen parkland. In Ontario, there's quite an extensive amount, also in Minnesota, quite an extensive amount of aspen decline, and this has been related to both prolonged drought as well as a forest tank caterpillar infestation that's lasted for a long period of time. I think in some areas it was over 10 years. Yeah, moving further south in the United States, in the states such as Colorado, especially Colorado, there's a lot of aspen decline, so much so that they've started calling it, they've named a syndrome after it, and they call it sudden aspen decline, or SAD. I think personally naming it syndrome SAD is sad in and of itself, but anyway, that's what they're calling it. So how did we get involved with this work? Well, back in the early 1990s, prompted by both public and by industry concerns about certain areas of forest that were dying back, Ted Hogg started a couple of studies, one in the Meadow Lake region of Saskatchewan, another one in the Grand Prairie region of Alberta, and these studies showed conclusively that drought was a major causal factor. And of course that raises concerns about the potential for impacts due to, with a changing climate. And I'm sure all of you know about the warming trend, and if you just think about how many years in the last decade and a half have been record warm years. So before I talk specifically about the CIFA study, what I'd like to do is just show you some of the analysis tools that we use. Of course, we have weather stations, mostly Environment Canada stations that we use, and of course with the forest monitoring side of things, we use aerial surveys, but primarily ground plots, just the typical forest type plots that everyone's used to. Another thing that we can use and have been using is remote sensing, both to augment our weather data set and also to provide us with things like land cover, as well as, excuse me, vegetation index or a forest health index. And through the process of interpolation, we can produce some gridded maps from both of these streams. If you do a process of an overlay, you can then start modeling various biological processes as functions of climate. And then if you apply various climate change scenarios, you can start making some predictions about what the future might look like for these various processes. So what I'm going to do is I'm going to talk about the forest monitoring side of it. I'll talk a little bit about the climate side of what data we use. I'll briefly mention some of the remote sensing, and then I'll talk about the results from the CIFA project. So as I mentioned, the CIFA project was started in the year 2000. It's a multi-scale design. It all the way from individual trees and tree rings, all the way up to number of trees per plot. We've got 2 plots per stand, 3 stands per site, and there's 25 sites across the prairie provinces. And these sites are in both the boreal forest as well as the drier aspen parkland. We designed it purposely like that. And we also have an additional 5 sites in Ontario that I'm not showing here. These sites are monitored annually, and they're in relatively pure aspen stands, and they're relatively young as well. They're between 50 to 90 years of age. And we were lucky in the sense that we just set the site up, and a year or two later we experienced a relatively massive drought through part of the region, which led to an increase in aspen mortality. What I'd like to do now is acknowledge our collaborators, which have been ESRD. They've been instrumental in doing the groundwork for all the Alberta sites for many years now. And our collaboration is working very well. And thanks to Mike Underschultz and Tom Hutchinson and others who have done all this work. We are also planning to do, as Mike briefly mentioned this morning, a similar type network for spruce, and we're trying to get that going within this next year or two. So what types of measurements do we collect from the ground? Well, first I'd like to say that repeated measurements, especially annual measurements, are really very important, especially for assessing rates of tree mortality. It's very difficult to assess rates of mortality from PSPs that may be measured only once every 10 years. You have to basically wait 20 years before you can even make any estimation of mortality. We also collect a lot of tree rings and tree discs so that we can compare the growth to drought and also to insect defoliation. And we do that every 4 years at each one of these sites. Annually, we measure tree health and using a measure of dieback, which is defined basically as the percent of the crown that's dead. So each tree gets a rating. And we also measure the incidence and severity of all the pests that we find on every tree. And finally, every 4 years we do a mensuration survey, and of course that's essential for quantifying not only the growth but also the losses, and as well is essential for scaling up beyond the plots to the landscape. So I'll briefly talk about the climate data. This is a map showing the map of Canada, showing the Environment Canada weather stations across the country through time, and I'll just let it catch up. And you can see that there are 3 major gaps. And one of them is historic. Prior to 1960, there were very few weather stations. Another one is that in the northern regions, the forested regions, it's really poorly represented by weather stations, as you would expect, where the population's low. And a third, and even more surprising gap, is the drop in stations, as you can see, after 1990. And this is due to fiscal restraints with Environment Canada. So right when we need this data the most, we're losing our ability to obtain it. So how do we fill in those gaps? Well, there are a number of other networks of climate stations. This is one called the Climate-Related Monitoring Program run by the Government of BC in consortium with a number of other groups. And it adds about 600 stations to our Environment Canada data set. And these stations are mainly from various government ministries, as well as BC Hydro and some private stations as well. In Alberta, there's a similar network. It's called ACIS, or the Agroclimatic Information Service. This adds about 200 and some stations to our network. And the quality of this data is really, really good. There's a lot of quality control. It's in some cases even better than Environment Canada's data set. The quality of the BC data is not as good, and you can spend a lot of time trying to fix some of those data problems. And I'm mentioning this to you because ideally at some point in the future it'd be nice if we could get our climate data from a single source at a single high standard, but we're a long ways from that yet. And those of you who have worked with any climate data have come to realize that you spend an awful lot of time with these data sets and just fixing errors, finding errors, and it can be really a bit of a nightmare. So what do we do with the climate data? Well, now I'm going to shamelessly promote a program that was created by Jacques Rainier and Rémi Saint-Germain from our Laurentian office in Quebec. This is a program called BioSim. And what it is, it's a temperature and precipitation-driven simulation tool, which allows you to model biotic and abiotic processes at almost any scale. So how does it work? Well, you basically feed the program with your location data, it could be either points or a map, and the program assembles the appropriate weather data and does a series of corrections and produces some historic data, the real-time data you can see on the graph there. And it can also use Environment Canada 5-day forecast for immediate predictions in the future, and also use normals, or even go with some GCM scenario data for if you want to predict well into the future. And then once the climate regimes or the temperature regimes are assembled, you can then push them through a simulation model. In this case, the graph you see there with the peaks, that is this is a phenology or development model for something like spruce budworm probably, and you can see that they've targeted the last instar. Each of these peaks represents the peak of a various instar of that insect, and they're targeting the last instar. And what they can do with this is then produce a map, just show them throughout their area of interest which areas are ready for or appropriate for spraying. So you can use any types of data. It could be a daily, weekly, monthly, annuals, normals, whatever you want. This is I've showed you an example of a gridded map here. This is one that was just from jack pine bugworm for an individual day I think it was in 2011. But you can also do this just for single points. And you can run this in near real time. So it'll produce products that are as recent as the weather database that you feed into it. And of course, as I mentioned, you can do forecasts. Now, it doesn't just have to be insect models. It can be anything that you can model with temperature and precipitation. For instance, it could be simple as degree day calculations across the landscape. And we've even now the developers of the program have built a large number of models for agricultural purposes. So a lot of crop development is now modeled like this. And this program is available for you free of charge. It's free to use and free to download. As well, at the same website here, there is the entire Environment Canada data set, and it's probably the most convenient place in which to obtain the entire data set, and that's updated every week. So any of you who are interested in working with weather data and climate, I strongly advise you to download this program and go to this website to get the database. So what do we do with climate data and biosim? Well, Ted Hogg has developed a simple index of moisture. It's called the Climate Moisture Index, or CMI, and it's really used for assessing drought severity in remote forested regions, especially where all you have is temperature and precipitation data. So the Climate Moisture Index is simply equal to the precipitation, which includes both rain and snow, minus the potential evapotranspiration, which of course is the loss of water vapor over a well-vegetated landscape. So this is an example of a climate moisture index map that was produced again with the biosim program. This is a 50-year mean ending in the year 2000, and as you can see, as what you'd expect, is that the southern grasslands are much drier than the boreal forest. I've overlaid the ecozone boundaries, and you can see there's some correlation between the two. And what we'd like to think is that the boundary between the boreal forest and the aspen parkland is actually the zero line for the climate moisture index, but there's some debate about that. So now we set up our sites, we put in our ground plots, all of them, all 25 sites across the prairies. In 2000, 2001, we started seeing some drought, especially in the south. So what happened in 2002? Well, that drought moved and quite far north, well into the aspen parkland and also well into the boreal forest. And it was so dry, in fact, if you look at the middle panel of that graph, you'll see the climate moisture index. It was the lowest it had been in 80 years. So, and that was due, you can see by looking at the top panel, mainly from a loss of precipitation, not necessarily an increase in temperature. But you can see in that bottom panel the general trend of temperature of an increasing by a few degrees from the period 1950 to 2010. And this is the climate moisture index for this area that's bounded by this polygon. And there was so much more, the drought was so strong in this area that a few years later we started noticing a lot of tree mortality in the aspen parkland between Edmonton and Saskatoon. And because of that, we decided to investigate this area a little bit further, and we started doing aerial surveys through this area, and that's what this polygon represents, is the area that we surveyed by air. And we also threw in hundreds of temporary ground plots in this site to measure this as well. So what I'm going to do now is just show you what the weather's been like for the remaining years from 2003 to the present. And what I'd like you to pay attention to is that Alberta, more so than the other provinces, has been experiencing some episodic, localized droughts in the last decade. So that was 2003. You can see 2004 started getting quite a bit drier in the south again. 2005, 2006, you can see the Grand Prairie region, there's a regional area of drought there. 2007, 2008, 2009 was really quite dry across the prairies, as well as, probably everyone remembers how dry it was in Edmonton that year. This is 2010. You can see there's drought again in the Grand Prairie region and along the Peace River, that chunk in the north. And 2011 and 2012. And if you look at this area up in the north, the orange area, that's along the Peace River Valley. So we suspect that that area, since it's had 3 years of really dry conditions, is probably going to start showing some mortality, and if not mortality, at least definitely some growth reductions. So a tool like the CMI allows you to plan your studies or plan your resources well, so that you can start determining what kind of effects the drought's having. And 2013 returned to a much more normal type condition. This looks a lot more like the long-term mean that I showed you at the beginning. So how does the drought lead to dieback? This is a conceptual model from Frey, and again, Ted Hogg was a co-author with this study. And the authors describe 3 types of factors: predisposing, inciting, and contributing factors. The predisposing sites would include things like the climate, basically where the site's located, successional stage, the ecosite, especially with regard to things like soil depth and water holding capacity, a stand age as well. The inciting factors, the 2 main ones, are defoliation and drought, although there are others. And finally, the contributing factors would be the typical forest pathogens that you'd expect to see in the forest. Now, if the drought's strong enough, you can get xylem cavitation, and you'll get rapid dieback and potentially rapid renewal. And we've actually saw that at a number of our sites. However, most of our sites have followed the second path, and that is you get this slow buildup of multiple stressors, which leads to a gradual loss of vigor, and you get slow decline and dieback. So what does this look like on the ground? Well, again, if you have these inciting factors, drought and defoliation, in and of themselves they can kill trees, and much as Mike Underschultz pointed out this morning, when you have these 2 events in conjunction or consecutively, that can certainly kill them off. Even if they don't kill them off, the drought and the defoliation will stress these trees, and then they become magnets for wood-boring insects. The wood-boring insects very often carry fungal pathogens, and the fungal pathogens colonize the trees, creating cankers, and of course that stresses the tree even further. Of course, there are other types of pathogens that can affect this, something like root rot, and if the stresses are strong enough, you'll get tree mortality. So this is a site that I'm showing some severe dieback. This is from our Patoche site. This is south of Prince Albert. In 2003, this is the photograph was taken a year after the drought came through, and you can see the trees will look pretty healthy. But if you look carefully, you can see there's a lot of light coming through. The foliage was very thin, the crowns were very thin in 2003. By 2005, most of these trees had died. Almost all of them had died. And when we looked at them and cut them down and examined them in detail, we could not find any of the typical forest pathogens. And so we suspect that this is one of those sites that died from xylem cavitation. In 2008, you can see that most of these trees had snapped off and fallen to the ground. You can also look and see there's a huge change in the understory vegetation. In 2012, you can see that there's a lot of regen that's popping up, and it looks relatively healthy. This is what it looks like from the air. This is a photograph taken in 2004. This is in the parkland area somewhere in Alberta. I'm sorry, but I've forgotten exactly where. But I've shown this photograph for a couple of reasons. One is to show you how extensive the mortality can be. It's just everywhere. And secondly, to show you that a lot of this mortality occurs in the fragmented aspen parkland itself. So you've got the forest fragmented by cropland, by natural grassland and rangeland. And this causes some issues and problems not only for locating and for measuring ground plots, but also for satellite imagery, because very often what you're going to get, the satellite signal is going to be a mix of the grassland and the crops, which may be relatively healthy, and these dead trees. Even with the larger stands, there are still other problems, and one of the main ones is that the dieback, when it occurs, is really patchy. It doesn't occur in large blocks at a single time. It's little, and you can see in this photograph in the middle there's a clump of maybe a single clone of aspen that's relatively healthy compared to what's surrounding it. And again, this has implications, especially for remote sensing, because again, you're going to get some mixing. You're going to get an averaging of these two when the sensor picks up whatever is reflected from the stand. So speaking about remote sensing, what are some of the advantages of remote sensing? Well, it retains the spatial heterogeneity. If in theory, it would be like putting a ground plot at every pixel. Another advantage, of course, is that it overcomes the lack of ground access, especially in northern regions where the roads are few and far between. Another advantage is that it's typically a lot less costly than putting in a large number of ground plots or doing even aerial assessments. And it also has the potential to supplement weather data. We're investigating the possibility of using MODIS system, or MODIS satellite systems, to using their surface air temperature to supplement those weather stations in the northern regions where you find there's typically very few stations. There are many challenges with remote sensing, and one of them is that the spectral response from dieback is really subtle. So it's hard to detect. It's much more subtle than something like fire or even defoliation. And another problem is the understory vegetation. You can get the crowns of these forests dying off, but the understory vegetation can be quite healthy and very green. Again, so you're giving a mixed signal to the satellite. Another problem is finding a compatible metric that you can compare the ground comparison to the remote sense metric. That's a difficult problem. And finally, the other issue is the spatial registration errors. These, I've shown a Landsat satellite here. The size of the pixel for the Landsat is about 30 meters, so 30 by 30 meters. But you can't be exactly sure about its spatial location, so that the standard rule is to take plus or minus 1 pixel, which means that now your window, instead of being 30 by 30, is 90 by 90. And when you have a pixel that's that large, especially since a lot of the aspen dieback occurs in patches much smaller than that, again, you get an averaging or mixing of the signal. So what are some of the common remote sensing indices? One of them is the normalized vegetation difference index. This is really just a measurement of how green the forest is, and the principle is simple. It's just that green forests will reflect more in the near infrared than the red, whereas forests that are dying off will reflect more in the, I may have said that backwards, but more in the red than the near infrared. But again, the problem is, if you have a healthy understory vegetation, this mixture, this switch in the spectrum may not occur, because of course the understory green vegetation is reflecting more in the near infrared than the red. So we started looking at some other processes by which to ascertain the impacts of climate. And one of them is to look at the canopy structure itself. And this is a canopy reflectance model. And what it basically does is looks at how the solar radiation is broken down into 3 components: the sunlit canopy, the shaded background, and the sunlit background. And it's the relative changes in these 3 components give you information about how the canopy has changed. And that's what we use to detect dieback. So this is what it looks like. This is a satellite image. I believe it's a Landsat image from the South Saskatchewan River, again near Batoche. This is in 2001. You can see there's some areas of light mortality. It's 2003, a little bit more. 2006, you can see there's quite a bit of mortality. You notice that it's all along, most of the severe mortality is along the west-facing slope of the river, which is exactly what you'd expect. And this is what it looks like from the air, and I believe this photograph was taken in about 2004 or 5. So we've had some promising, some tantalizing progress with remote sensing, but we're still not quite there yet. So it's going to take quite a bit of work to allow us to apply this over large landscapes. Now I'm going to pull all that together and talk about the information from the ground, the remote sensing, as well as our climate data. This is a graph showing the stem mortality across all of our sites, not just those in the drought regions, but also those that experienced no drought. And what you can see is that we've increased from roughly around 2% stem mortality to well over 4%. And you can see it's dropped back down recently. And the other thing to notice, of course, is that there's a lag with the peak mortality of about 5 to 6 years on average. And there's so much mortality in our sites that we've lost 48% of our trees that are now dead. And that translates into an average basal area loss of about 31%. This is something we're working on quite recently. We've just submitted this for publication. This is looking at the fall down rates of those dead trees. How quickly do they fall to the ground? The black bars represent dead trees, standing dead trees that have their dead crowns intact. The hatched bars represent standing trees that have had their dead tops fallen off. They've snapped off and fallen down. And the white bars are those trees that have snapped off below breast height, below 1.3 meters. And what you can see is there's a relatively fast fall down rate. And so much so that after about 5 to 6 years, you've lost about 80% of those dead crowns. They've disappeared, they've fallen to the ground, and you just don't see them, whether it's from the air, from an aircraft, or from a satellite. And we found that this relatively fast fall down rate is related to wind. And of course, the wind is generally stronger in the parkland than in the boreal forest. It's also related to age and Phalaenus tremulae, the decay fungus. And of course, those two are correlated. But interestingly, we found that this fall down rate is not related to the moisture, to the climate moisture index. Mortality is, but the fall down rate is not. Of course, this fast fall down rate has implications for not just ground monitoring, but also remote sensing, and as well for carbon cycling, because these trees that have fallen to the ground are going to rot a lot faster than those trees that remain standing. This is a graph showing the change in the live biomass. Again, this is for all of our sites across the entire network, both those that were in the drought region and those that weren't. And what you can see is that following drought, I should say first of all that the green bars above the zero line represent the increase in biomass due to growth, and the gray bars represent losses due to mortality. And then, again, what you can see is following drought, you get a reduction in growth, and you get an increase in mortality. And this is the net annual change when you look at it. So in some years, these forests stop being a carbon sink, and they end up being a carbon source. What I'm showing here, this is the differential response to drought. This is looking at the percent dead biomass, again, the above ground biomass, compared to the minimum CMI for each of these stands. And what you can see is that predisposing factors matter. These sites that have relatively high dead biomass, those are probably sites with poor soils, or maybe very aged stands, or may have some other issue, may have had defoliation and so forth. So the predisposing factors make a big difference. When the moisture is limited. When it's not limited, you can see there's hardly a range at all in the rates of dead biomass. So now focusing solely on the intensive survey area, the area that we surveyed by air. In this area, there's a total of about 11.5 million hectares. About 3 million of those are forested, and we found in that area, we estimate there's a total of 45 megatons of dead above ground biomass, and that represents about 20% of the total biomass. If you break it down by ecozone, the parkland ecozone had much more than twice the percent dead mass as the boreal forest. And in effect, and this is these data were collected in 2006. So in 2006, 35% of the aspen in the parkland of that polygon area 35% of the above ground biomass was dead. It was just dead trees. And based on our sites outside of the drought area, we estimate that the normal figure for this should be around 7%, which leads us to the conclusion that out of that 45 megatons that I've told you we've had in this area, 29 of that is due to drought. And that translates into about 14 megatons of carbon, which is about 7% of Canada's annual CO2 emissions for the year 2007. So with that, I'd just like to conclude by just drawing your attention to a few things. First of all, as I've mentioned, the drought-induced forest decline is a growing global concern. And we've had a lot of mortality in Western Canada, primarily in the Aspen Parkland. And the dieback is often very, very patchy and fragmented, and it often occurs in a fragmented landscape. It's not just a solid landscape. And the decline itself and the quantification and detection of it is also hampered by the fact that the mortality is delayed. So, years after the drought, then you start seeing the mortality. As well, the trees fall down relatively fast. So again, that hampers the quantification and detection. And however, you can use simple indicators like the climate moisture index to at least direct your resources and help you predict where you might see drought-induced mortality. And finally, I shouldn't say finally, but the second last point, that remote sensing is a useful tool, but it has its limitations. And we've been struggling with this for over a decade, trying to get it to work very well, and it just hasn't yet got to that point. But overall, the real take-home message for this is that if you really want to assess the impacts of climate on forests, you really need to do a multidisciplined, multi-scaled approach. You need to look at ground measurements, remote sensing measurements, climate and aerial surveys and so forth. And those things are essential for not only the detection, but also for the scaling up and the quantification of the types of damage you have. So with that, thank you very much. Are there any questions? I didn't think so. Thank you. Yeah, sure. Yes, thank you. Oh, sorry.